Hello, so we'll finish the chapter 12 review, and so we'll go over how to find out the molecular geometry or the shape of the molecules. And for this, you will need this table that you see now. It's part of the document that is called electronegativities and molecular geometries. So it's that Word document here. And let me show you where to find it on Canvas. So on Canvas, it's in chapter 12 module, it's called Electronegativities and Molecular Geometry document. So you want to take this document out when you are doing this homework or this review, and when you're doing the homework as well. So that's the document we will use. So last 2 times we did the Lewis structures for several molecules. I've listed the molecules here on the left side. So again, the subscripts are not formatted properly. I cannot do that. And then you have the Lewis structures. So PCl3, Cl2O, HCN, then the sulfate ion, P2H4, and then on the right side, C2H4, H3PO4, and then HCO3 -1. So we have the Lewis structures, and that's what you need when you need to decide the molecular geometry. And so first you have to draw the Lewis structures. And then you will use the table that I showed you earlier to decide, according to the number of electron groups you have around the central atom, you will decide the shape around that central atom. So you have to always decide what is the central atom you're looking at and count the electron groups around that atom only. So for example, PCl3. So the central atom here, it's easy. There is only one, that's P, right? P is in the center. It's surrounded by the 3 chlorines. And so we will count now the electron groups. And so an electron group is either a single bond, a double bond, a triple bond, or a lone pair on that central atom. And so here P, we can see that it has 3 single bonds around it and then 1 lone pair. So we can say that PCl3 has 4 electron groups around it. So 4 electron groups around P. And so now we will go to that table. So we have 4 electron groups. And so we need to look at the left column here that says number of electron groups. There's either 2, 3, or 4. So here we want to look at the rows where you have 4. Then you need to count among those 4 electron groups the number of lone pairs you have that are included in those 4. And we had 1 lone pair and 3 single bonds. So here you want to go in the row where it says 4 electron groups, 1 lone pair. And you follow going to the right, and you see trigonal pyramid is the molecular geometry. And then you have a model showing that trigonal pyramid. And then you have the bond angles. The bond angles are the angle between 2 consecutive bonds. And in the case of this trigonal pyramid, it's less than 109.5. So this is important here to recognize that there is a less than in front of the 109.5, because in sapling, this can give you trouble if you do not include the fact that it's less than 109.5. Sapling will not count this right. So be aware of that. Here, it's less than 109.5 because it's because of that lone pair here, it kind of distorts the angle from the tetrahedral geometry, because really it comes from the tetrahedral geometry, but the top atom is now a lone pair, and that will change the angles slightly. So again, for sapling learning, it is important to put the less than 109.5 when you have a trigonal pyramid molecular geometry. So we said we have a trigonal pyramid geometry. So now we need to draw this. That's what the question 11 was asking, is to draw, to determine the molecular geometry and then draw it. Okay, so how do we do this? We have the P for, so let me draw this here, P. I will have P here. And then the 3 chlorines will be downward because it's a pyramid. So the P is like at the top of the pyramid, and then it's a trigonal base, right? So we'll have 1 Cl in the plane on that side, and it could be on the other side, it doesn't matter. Then we draw a bond, and that bond, the way I draw it, it means it's a bond in the plane. So we have P, Cl, and the bond here in the plane of the paper. And then we need to draw what we call wedges. And so the 2 wedges, you will do them on the other side, and one will be completely filled. So you darken it. And then the other wedge will be just parallel to that first wedge on the same side. And this one will be hashed. So you just put some stripes, if you will. And so those 2 wedges, always draw them on the same side, downward, and parallel to each other. And then you give them chlorines. 1 chlorine and the other chlorine. So that's how we draw a trigonal pyramid structure. And to justify that trigonal pyramid structure, I like that you show the 2 lone, the 2 electrons, the lone pair on P, because this really justifies why we do have this shape. It's because of the lone pair there. We have 4 electron groups, but one of them is a lone pair. And so that creates this, it's from a tetrahedral geometry, but then you remove one of the bond. It's not visible anymore, it's a lone pair. And so that's why you only have the base of the tetrahedron, and then it stops. And so then it looks like a trigonal pyramid. So that's for PCl3. Let's do Cl2O. You see Cl2O here. So the central atom is oxygen. So let's count the number of electron groups around oxygen. And let me change color so we can differentiate here. So oxygen is the central atom. It has 2 single bonds around it and 2 lone pairs. So again, 4 electron groups around oxygen. Right? Each single bond counts for 1 and each lone pair counts for 1. So we have 4 electron groups around oxygen. And so that's going to be, again, starting from a tetrahedral shape. So let's look at the table. So we have, again, 4 electron groups around the central atom, but this time we have 2 lone pairs. So you will look at the lowest row here. So starting with 4 electron groups, 2 lone pairs, it says it's bent. And then the angle is again less than 109.5. So again, you need to specify that less than 109.5. And then the model here is the model of the molecule of water, which is bent like that. And because the oxygen also has 2 lone pairs on it and then 2 single bonds. So, those 2 lone pairs have a shape of the tetrahedron, but because it's lone pairs without any atoms bonded, then you don't see that. And that's why it looks like only a bent molecule in the end. no, this. Okay. Oh, so here we have the table, and we said we have 2 electron groups around the carbon. And so we will look at the first row here where you have 2 electron groups, 0 lone pair. And so it's a linear molecular geometry. And we can see here the 3 atoms are in a line, and there is an angle of 180 around the the carbon in our case. So it's a a line. So it's a linear molecular geometry. So we said we have a linear geometry. Oh, can't write anymore. Linear. So linear, and so that means the shape as you have it here stays the same. HCN, you have the hydrogen, the carbon, and the nitrogen all in one line with an angle of 180, between the CH bond and the CN bond. And so it stays like that. Because to draw bonds in the plane, you draw them as straight lines. So that is the 3D conventional way that chemists would draw a linear molecule. So let's do SO4, the sulfate ion now. So we have, and I have to write now. So S is the central atom. It's surrounded by 4 single bonds. So for S, we will have 4 electron groups around S. So let's look at the table to decide what geometry we have. So we have 4 electron groups, 4 single bonds, which means 0 lone pair. So you will look at the row where it starts with 4 electron groups, 0 lone pair, and it's a tetrahedral shape. And you see the tetrahedron modeled here. And the angle is 109.5 exactly this time. And that's exactly that angle when all atoms that are bonded to the central atom are of the same kind, which is the case with SO4. So we have a tetrahedral geometry. So it's tetra. Oops. Tetrahedral geometry around S. So let's draw this now. So we have S in the center, and you will put 2 oxygen in the plane, and I'll put them like this. So we know they are in the plane because we draw straight lines between the sulfur and the oxygen, and when we have a straight line, that means it's a bond in the plane. So we have 3 atoms in the plane, 2 oxygens and the sulfur. And then we will draw those wedges like we did earlier, 2 of them on the same side, parallel. Okay, I'll make this one full. And this one, I will give it stripes. So a hashed one and a full one. Let me make it thicker here. Okay. So we have our 2 wedges. You draw them parallel to each other, downward, and on the same side. And then we have the 2 other oxygen bonded there. And so I don't know if I said that earlier, but the wedge that is full represents a bond that comes towards you. So compared to the plane of the paper. It's a bond that comes towards you, and the wedge with the stripes, represents a bond that goes behind the paper, away from you. And so that's the tetrahedral shape. I will not draw the lone pairs on the oxygen, that would be too much. And sulfur doesn't have a lone pair, so then we'll leave it like this. So that's the tetrahedral shape of the sulfate ion. So let's do P2 H4 here. So let's find another color here. So let's count the number of electron groups around the central atom. So here you have two central atoms. Each phosphorus is a central atom, and they are equivalent. The shape you find for one of the P will be the same for the other P. So you can focus on one of the phosphorus and count the electron groups around that one. So each phosphorus is having 3 single bonds, right? One single bond to the P, and then 2 single bonds to each hydrogen. So that's 3 electron groups plus the lone pair on the P. So that's 4 electron groups. So we can write that 4 electron groups around, around P. One at a time. So always count one at a time. So 4 electron groups around P. So let's see with the table now what kind of shape it is. 4 electron groups and 1 lone pair. So we have 4 electron groups, 1 lone pair, right? 3 bonds, 1 lone pair. So you start with the row that says 4 electron groups and then 1 lone pair. And it's again trigonal pyramid. We have one molecule with that shape already. And so the bond angle is less than 109.5. So the two phosphorus have that trigonal pyramid shape. So we said trigonal pyramid. Okay, so it's trigonal pyramid, and we have 2 of the phosphorus like that. So we'll draw the 2p in the plane, and we'll put yes, the 2 p's in the plane, and that means the 2 hydrogens will be drawn with wedges. So let me show you how we would do that. Let's see. No. So, okay, one of the P would be here. And then we do a straight line for the bond in the plane. And we'll show the lone pairs here to show which way the pyramid will go. So it's not gonna be exactly the triangle of the base of the pyramid will not be flat, you know, horizontally, because here this bond is, you know, tilted up. And so the wedges will have to go really downward. And so you have to tilt your head and tilt your head to the right when I'm doing this one. So let me redo this wedge. It's a bit... okay, so that's going to be the full wedge here. So if you're tilting your head, you can see I'm starting a pyramid there. And then the other wedge, always make them parallel to each other, downward. But you see how it's a bit more downward than what I did above for the sulfate, for example. And so each of these wedges, they are bonds that are bonded to the hydrogens. And then we do the same thing on the other side because it's the same shape, but downward, but more towards to the left. So downward. Oh, it's a bit too thick. So okay, so that's the full wedge. Bonded to an hydrogen. And then the other wedge with stripes. And that's also bonded to an hydrogen. So that's how you would do the shape of P2H4. So you see, if you tilt your head for the left phosphorus, tilt your head to the left, and you see how we recognize the trigonal pyramid. And then for the phosphorus on the right, tilt your head to the right, and you recognize the trigonal pyramid there. So that's the shape of P2H4. So we'll continue on the right side here with C2H4. So again, it's very similar to P2H4, except that in the center we have carbons, but they are also equivalent. What you decide for one of the carbon will be correct for the other carbon. So let's focus on one of the carbon. And so we have two single bonds, to the hydrogens, and one double bond to the other carbon. So that's 3 electron groups. 3 electron groups around the carbon. Okay, 3 electron groups around the carbon. So let's see now with the table what shape does it give to the molecule. So we said we have 3 electron groups around each of the carbon. And so you will look at the row where you have a 3 and we have no lone pair. So 3 electron groups, 0 lone pair. You want to look at that line. And it says trigonal planar. And you see so that it's in the shape of a triangle with the central atom in the middle of that triangle. And it's a flat structure. That's why it's called planar. Planar means it's all 4 atoms are in the plane. And for the electron groups to be as far away from each other as possible, the bonds are having bond angles of 120 degrees. So each consecutive bond is separated by 120 degrees. So we have a trigonal planar. So to not confuse with trigonal pyramid, right? It's very different shapes. Trigonal pyramid is not flat. It's like a pyramid with a triangle at the base. A trigonal planar structure is flat. So that means you can draw all bonds in the plane with just straight lines because all atoms are in the plane. So for this, that will look like this. And I'm sure you've seen something like that before. So you would draw the C's with the double bond in the center. And then make sure you do angles of 120 around that central bond. And then each of these bonds, contains a hydrogen. And so we have 120 degrees between each bonds. And so again, remember how when you decide for one of the carbon, it is the same result for the other carbon. So that's why it's a symmetrical shape like that. And it's flat. All atoms are in the plane. The 4 hydrogens and the 2 carbons are all in the same plane. So let's do the phosphoric acid here with H3PO4 drawn below. So we have more than one central atom there. There is P, obviously, that's the central atom. So let's do the the molecular shape of around P. But you will see also that every oxygen that is bonded to an hydrogen can also be considered a central atom. And so we'll do that after. So if we look at P, we have 4 single bonds around it. So that's going to be 4 electron groups around P. So here I have to specify that it's around P because we have 2 kinds of central atoms. So 4 electron groups around P. Let's look now at the table to see what is the shape. So when you have 4 electron groups and 0 lone pair, it's a tetrahedral shape, right? Look at the row where it starts with 4 electron groups, 0 lone pair, tetrahedral shape, and the angle is 109.5. So we have a tetrahedral shape around the phosphorus. Now we need to decide what is the shape around each of the oxygen that is bonded to an hydrogen. So let's look at that. And I will use a different color here to really show that it's not the same central atom. So if we focus on one of the oxygen, and if you look at them, they are all the same. Those 3 oxygens that are bonded to the hydrogen, they will, you will obtain the same shape for each of them. So let's just focus on one. And so if you look at one of these kind of oxygen, there is 2 single bonds, 1 bond to the P, 1 bond to the H, and then 2 lone pairs. So that means 4 electron groups made from 2 single bonds, 2 lone pairs. So 4 electron groups around O. And O, we know it's the O bonded to the H. So let's look at the table. So we said 4 electron groups, 2 single bonds, 2 lone pairs. So you want to look at the bottom row here. That starts with 4 electron groups, 2 lone pairs, and we have a bent shape around that oxygen. And the angle is less than 109.5. Okay, so bent shape with an angle of less than 109.5. So we said that the shape around the oxygen that are bonded to the hydrogen have a bent shape with an angle of less than 109.5. Okay, so now we need to draw the full structure. The way that we need to do it conventionally. So we'll try to have as many bonds in the plane as possible to make it easier for us to draw, right? And so we can have, 2 oxygens that have hydrogens in the plane, and then the oxygen that is by itself, and another of the oxygen with the hydrogen will be with wedges. So we need enough room, so give yourself enough room. So I'll put the P, so let me put first the oxygen. I'll put 1 oxygen here. It will be bonded in the plane to the hydrogen because it will have, 2 lone pairs there. 1, 2, 3, 4. And then bonded straight down to the phosphorus. That's going to be the top of my tetrahedron here. On the left side, I will put the other bond in the plane with another oxygen here. And then I will make it a bent shape with the hydrogen for that. And I will put it also in the plane. And so the 2 lone pairs then are downward here for that oxygen. And you can recognize the bent shape for the oxygens, right? Each of the oxygens I've drawn here have a bent shape. And that's because of the 2 lone pairs. So now we need to do the wedges for the tetrahedron that, you know, has P as the central atom. And so that's one of the wedge. It's the full one. And then let's do the other one parallel to it, downward again, with stripes. Okay. And so each of these have an oxygen. Let's put one oxygen here, the other oxygen there. But one of these oxygen has a nitrogen bonded to it. So, but these oxygens are not in the plane anymore, right? The filled wedge represents an oxygen coming towards you compared to the plane of the paper. And the hashed wedge, or the one with the stripes, represents a bond that goes behind the paper. So behind you, away from you. So I'll draw the other hydrogen there. And, you know, we don't know really how to do this, but we can do it like this. You can do a wedge that goes away also, and where you have the hydrogen bonded to the oxygen. Right. And so that oxygen has two lone pairs there. And of course, the fourth oxygen has lone pairs, but I will not draw them because that would be too much. Okay, because anyway, it's not, you know, the shape, it doesn't add anything to the shape to have the lone pairs on that single oxygen. So it's more important to show the lone pairs on the central atoms. And here, each of these three oxygens that are bonded to hydrogens are considered central atoms. So that's why I draw the lone pairs on those. But you can omit the lone pairs on the fourth one because it's not a central atom. And so, you know, that's our phosphoric acid there with this weird shape. But you see around P, the tetrahedron, and then around the oxygens that are bonded to the hydrogen, you see how they are bent. So that's for phosphoric acid. Finally, we have the hydrogen carbonate ion, or what we also call the bicarbonate ion, just to the left here. So let's find another color for this one. Okay, so let's count the number of atoms around the carbon. Carbon is the main central atom here, but there is also one of oxygen that can be considered a central atom. So let's do carbon first. We have two single bonds bonded to carbon and then a double bond. So that's three electron groups around C. Oh, let's redo that. Around C, okay? And let's do the oxygen also here. Oxygen that is bonded to hydrogen is also having a shape. And so we can count the number of electron groups around that oxygen. And so it has two single bonds, a single bond to carbon and a single bond to hydrogen, and two lone pairs. So that's 4 electron groups around this oxygen, 4 electron groups around that oxygen. Okay. So let's look at the table now. And so for carbon, we have 3 electron groups, no lone pair. And for the oxygen, we have 4 electron groups, 2 lone pairs. So we said the carbon is surrounded by 3 electron groups, 0 lone pair. So you will look at the row where you have 3 and then 0 lone pair, and it's a trigonal planar shape with 100 degree angles between the bonds. So trigonal planar for the carbon, and then the oxygen that is bonded to the hydrogen, we said had 4 electron groups, and 2 of these electron groups are lone pairs. So you look at the bottom row here, 4 electron groups, 2 lone pairs, that's a bent shape with an angle of less than 109.5. So let's go back to our drawing. Okay, so we have a trigonal planar shape around the carbon because we have 3 electron groups, no lone pair, so that's trigonal planar. Around the oxygen that has a nitrogen bonded to it, we have 4 electron groups, 2 lone pairs, so that's a bent shape with an angle of less than 109.5. So let's draw the hydrogen carbonate according to the 3D convention that chemists use. So we have a trigonal planar shape for the carbon, so that's easier to draw. And then we will have to do a bent shape. But everything can be in the plane, right? Because the 3 oxygens and the carbon are in the same plane due to the fact that it's trigonal planar. And then because it's bent, we can put the hydrogen also in the plane, so let's do that. We have the carbon in the center, 1 oxygen here, another oxygen there, the third here. So try to space them by 120 degrees. So one of the oxygen is bonded by a double bond to the carbon. And then here we have a bent shape. So let's give it a bent here. And then this oxygen has 2 lone pairs, which is why it's a bent shape for that oxygen. And then we have a trigonal planar around the carbon. I could have drawn this maybe, slightly more straighter, but you have the idea here. And we don't need the lone pairs on the 2 oxygens that are not bonded more than to the carbon. And I only need the lone pairs on the oxygen that is bonded to the hydrogen to show why we have a bent shape there. And so that is the structure, the 3D shape of the hydrogen carbonate ion. And so that ends the chapter 12 review on the molecular shapes.